Here we're going to look at question 2 from section 2 of the ENGAA specimen paper. So in this question we're given two different blocks, x and y, and they're placed at the top of two different slopes. We're told that they slide down these smooth slopes at a height h. And then the question asks us, how do the times taken and the velocities of our two masses, x and y, compare after they've been released and after they've slid down to this height h? So if you would like to have a go at this question yourself, then please pause the video now, otherwise let's have a go at it. So to do this question, let's first have a bit of a think about the times it's going to take for our blocks to slide down. Now we haven't really got any variables here, so we don't actually have to do too much math to try and think about this question. What I think is a really good technique is to try and think about some of the extreme cases of this slope. So we're looking at two different steepnesses of slope. What about if we consider the absolute extreme cases where we have one slope which is absolutely horizontal and one slope which is absolutely vertical? And let's see how our block's going to behave on these two cases. And this should indicate how it's going to behave on these two surfaces. So if we look first at our horizontal slope, then we know that our block isn't going to accelerate anywhere at all. It's just sitting on a slope just like it would be sitting on a table. It's exactly the same case, so it's going to be stationary. And since it's stationary, it's going to have absolutely no acceleration. Right, now if we look at our block on an absolutely horizontal slope, then remembering this is a smooth slope, just like these ones are up here, then there's going to be no friction at all. So if the acceleration due to gravity is just going to be g, then our block is going to accelerate at g. So what about then if we consider something in the middle, where we have a slope which is at some sort of angle, not quite horizontal, not quite vertical just yet? Well, as you'd expect, it's going to accelerate at some different acceleration, at some rate, but it's not quite going to be, it's not going to be 0 and it's not going to be at g either, so it's going to be somewhere in between the two. Now, thinking about this, then of course it would make sense that the steeper the slope gets, the closer your acceleration is going to get to g, and the shallower it gets, the closer it's going to get to 0. So a steeper slope, it's going to have a block which accelerates faster on it. Now, if we go back up and look at our two blocks, then we can see that y is on a steeper slope. So therefore, it's going to accelerate more than x is going to. So if x accelerates less, then as you'd expect, it's going to take longer to travel down the slope. It's going to take longer to get up to speed, and it's just going to take longer to get down. So the time it takes x to fall this height h is going to be larger than the time it takes y to fall down that height. Now, something which is interesting here is that the mass of the blocks doesn't matter whatsoever. So this is just for the simple fact that something falling, or things falling all fall at the same rate. It doesn't actually matter what their mass is. So while this is sliding, it's just like resisted falling, if you like. There's going to be no sort of mass component to it whatsoever. Now, if you did want to try and get a bit more mathsy with this question, then you could try and look at the forces on our blocks. So we'd have a weight acting downwards, and there'd be a component of this weight acting along the slope, and this is what would accelerate our block. Now, this is going to have a weight component in it. When we find the acceleration using Newton's second law, the mass components are going to cancel out. So the acceleration is actually just going to be equal to g multiplied by the sine of the angle. But you don't actually have to do that. It's kind of overcomplicating the question. I think thinking about the extreme cases is absolutely all you'd need to do. Okay, so now that we've thought about the times, let's go on and look at velocities. So how could we do this? Well, the easiest way is probably going to be conservation of energy. So we know that our blocks start with this same potential energy. They're both at the same height and are going to have the same potential. Now, this potential is going to be converted to kinetic energy at the bottom of this height. So, since they have the same potential at the beginning, they're going to have the same kinetic energy at the bottom of the height. And if they've got the same kinetic energy, that means that they're going to have the same velocities. And therefore, the two velocities are just going to be the same, so Vx equals Vy. Now, this is actually simplifying it slightly, in that here I've really assumed that the two masses are the same. But if we were to do this mathematically, then we'd see that the mass term actually cancels out when equating the potential and kinetic energy. So they will have the same velocities anyway. Which, if you're interested in finding, should just be equal to the square root of 2g over h. But again, it's overcomplicating the question. It's quite a simple, just 1 mark question. So with these times and velocities, we can go ahead and look at the answers in our question, see that they correspond to D.